Section 1.2 talks about Gaussian elimination, and we start off with this definition of reduced raw echelon form. Now, for theory, this is very important, but for actual computation, this is a lot of work. We're not going to really be doing that much. We're going to use echelon form, but not reduced raw echelon form. So here's the definition, and it starts by for a matrix to be in reduced raw echelon form, 4 things must happen. 1. If a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. And just a reminder, if you're looking at a matrix, these are the rows. So you look at them sideways. When you look the first entry, if it's not a 0, it has to be a 1. 2. If there are any rows consisting of all zeros, you want them to be at the bottom of the matrix. 3. In any 2 consecutive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the one leading higher than it. That means something like this. The one in the second row should be to the right of the one above. And for each column that contains a 1 has zeros everywhere else above and below. So if there's a 1 there, there should be zeros above and below it. Now, a matrix that has the first 3 properties is said to be in row echelon form. Thus, a matrix is in reduced row echelon form is of necessity in row echelon form, but do not work conversely. So, reduced row echelon form if you have all of these 4. If you have all 4, automatically you are in row echelon form. So, row echelon form, the first 3 conditions must be satisfied. The last condition pretty much says each column that contains a 1 has zeros everywhere else in the column. So, if I look at example 2, it says determine whether the matrix is in raw echelon form or reduced raw echelon form. So I'm looking at 1, I notice, 2a I mean, there's a 1 there, well okay, and the zeros are all on the bottom. So I notice this satisfies property 1, 2, and 3, so we say this is in raw echelon form, but since the property 4 is not satisfied, because above this one there's a 2. Therefore, property 4 is not satisfied. So if I called raw echelon form, how am I going to write this? Let's say R for raw echelon form, and for reduced, I'll call reduced. So this is in raw echelon form, but it is not in reduced raw echelon. B, if I look at B, I notice that that's a 1, that's a 1, that's not even a 1, that's a 2. Automatically, this is not in raw echelon form, and it's not in reduced raw echelon form either, automatically. To be reduced raw echelon form, it must be in raw echelon form first. Now I look at C, I notice there's a 1 there, very good. There's a 1 there, very good, but the same issue. The third column, there's a 4 above it, which means that the matrix is in raw echelon form because the zeros are down there, but it's not in reduced raw echelon form. So this is raw echelon form, yep, but it's not reduced. So reduced, you want anything above and below the ones to be a 0. I look at D, that's a 1 right there, that's a 1 right there, everything is a 0. First 3 properties are satisfied, so this is in raw echelon form, but since that's a 5, this is not in reduced raw echelon form. I get to E, and in E I notice the 0 row is not on the bottom, right? So this is not in raw echelon form, automatically not in reduced. I go to F. If I look at, that's a 1, that's a 1, that's a 1, and the zeros on the bottom. So I notice that this one is right underneath that. Remember, the ones had to be to the right if there was another one. So this doesn't satisfy the second property. Automatically, this is not in raw echelon form, and therefore it's not in reduced raw echelon form. Here I see a 1 right there, and I see 1 right there. So the first entry of each of those is a 1. Below that is a 0, and above that is a 0. This is in reduced raw echelon form. If it's in reduced raw echelon form, it's automatically in raw echelon form. Now, you don't need to pay really a lot of attention to this. You want to pay attention to the row operations that we're going to do. So let's see how this plays. It says, suppose that an augmented matrix, again, I know they don't do that, but I'm going to do that. Suppose that the augmented matrix for a linear system has been reduced by row operations to the given raw echelon form. Identify the pivot, rows, and the column and solve the problem. All right, well, let me tell you what's so important about the echelon form. Now, we're going to be more interested in pivot columns than pivot rows, but let's talk about that. So rows, you look this way. You look at the first row. You see a 1, that's a pivot, and that's called a pivot. You don't look at the coefficients or the constants, the ones after the equal. So this has 3 row pivots, and if you look at the columns, you look vertically, that's what you have to really worry about. This is the part that's not going to leave us alone. If I look at this, now once you have a pivot in a column, automatically the first row doesn't count anymore. For you to have another pivot, it has to be in the second and in the third. So this has 3 pivots in the columns, 3 pivots in the rows. If that's the case and it's a 3 variables, then automatically you'll say x3 equal a 7, x2 equal a 0, and x1 equal a -3. And that's why reduced raw echelon form is really important, because just by looking at the problem, you could figure out what the solutions are. And you don't have to do any work. But the issue with it is, to go from a traditional matrix to reduced raw echelon form, that turns out to be a lot more work than we like. If I look at this problem, let's talk about row. That's 1. Again, that's another. So this has 3 row pivots. Columns. Column 1. Again, column 1 doesn't count anymore. Column 2 and column 3. Now, isn't this x1, x2, x3, x4? That means there's an extra 0 row there. You always try to make it matching the columns, the column variables. If you're missing 1 row or 2 row, that's when you come in and say, well, look, that means x4 could be anything. And now if you go back and say, this is x3 plus x4, which is t equal -5. So x3 is 5 minus t. You go to this row, you say, well, look, there's a pivot. x2 plus 3, again, t equal 2. So x2 is 2 minus 3t. And x1 up there, you say x1 minus 7t equal 8. So x1 would be 8 plus 7t. There it is. And the solution will be t, 5 minus t, 2 minus 3t, and 8 plus 7t, where of course t could be any number you want. If I get to this problem, again, talk about row pivots. There it is. 1, 2, 3. That's it. 3 row pivots. Let's worry about the columns, and that's really the crucial part that you want to pay attention to. There is 1. That row doesn't count. There is 1. There is 1. And that's it. x1, x2, x3, x4, and x5. Well, there's 5 of them, and I only have 3 pivots, right? So what that means, I'm gonna have x5, you notice it doesn't have anything. We're gonna call x5 a t. And do you notice where the other non-pivot is? Color didn't. Here we go. Didn't pick up. And x2 is gonna be, let's say, look, I think like S or C. Let's go with C. Okay. And now what? Now you're gonna go to this and say, look, x3, x4, I'm sorry. Again, it's right there. Ah, boy. Okay, one more time. Get registered. This is 1x4 plus 5. Well, we already said x5 is going to be t equal 8. So x4 is 8 minus 5t. We have x5, we have x2, we need x3 and x1. x3 is right there. Again, it's right there. So 1x3 x3 is going to be 7 minus 4x5, which is t. I got it. So we have x2, x3, x4, x5. Let's go to x1. x1 minus x2. We said x2 was c, minus 6c, plus 3x5. That's 3t equal negative 2. So we'll say x1 is negative 2 plus 6t minus 3, minus plus 6c minus 3t. And if I wanted to write the solution, should have given myself a bit more space, I would write the solution as follows. I will use x5 is a t, x4 is 8 minus 5t, x3 is 7 minus 4t, x2 is a c, and x1 is negative 2 plus 6c minus 3t. And now x1, x2, x3, that's nothing more like x, y, z, w, and whatever those are, depending on the author and the book. How about this problem? Okay. If I look at D, I have one row, 2 rows, 2 row pivots, but columns, I have one, that's x1, x2, x3. I have one, and again, 2, only 2. Do you notice that x2 doesn't have any? Then this is how we're going to start writing the problem. x2 could be free, or we call it t. Oh, I didn't pay attention to that. We have no solution. I was going to proceed and go on. This row here says 0x plus 0y plus 0c, or 0x1 plus 0x2 plus 0x3 equal 1. That means 0 equal 1. This is inconsistent. Now, if it was consistent, I would have proceeded like I was doing. So tradition, those we're going to repeat over and over. You want to pay attention to when you have no solution and when you have a solution, how that works. Now we want to get to this problem. All right, this is where we really want to start paying attention to how this plays. We would like to solve this using Gaussian elimination. Let's talk about Gaussian elimination. You write this as an augmented matrix. 2, 2, 2. And again, you don't have to put that line. I do. That's only me. So this is kind of like when you do syntactic division. Every time you use Gaussian elimination, our goal is to make those 3 a 0. That's it. That's all we do. Even when they ask us to do raw echelon form reduced, we just stick with this because this is the most efficient. And let me color code those. It takes 2 steps. Step number 1, you're going to get the red to be 0. And step number 2, you're going to make the green equal 0. And it has to be in that order. So to make the red 0, to make this a 0 and this a 0, if I add this to this, that will be a 0. You have to tell me what you're doing. you're taking row 1 and adding that to row 2. And it's very important to tell me where are you going to put the result. Since you want the 0 right there, you're going to put the result in row 2. So what this does, this tells me exactly what you're doing. You're adding that to 2 minus 2 is a 0. 2 plus 5 is a 7. 2 plus 2 is a 4. And 0 plus 1 is a 1. Then you want to make this a 0. How do you do that? Now, I could say take negative 4 row 2 plus row 3. Again, if I multiply this by a 4, wouldn't that become a negative 8 plus 8? Or you could say multiply this by a negative 4 and add it to the bottom row. It doesn't matter how you do this. If I multiply this by a negative 4, that will be negative 8 by 4, positive 4. 4 times 20, 4 times 2 is 8, and 4 times 1 is 4. Again, let me show you what we're doing. To make that a 0, that, I'm multiplying this by a 4, that makes it negative 8, and I'm going to add it to this. And I'm going to put the result in row 3. I'm going to put it here, so that's a 0. Well, this is 8, 1, this is row 3. If I add those, what do I get? I get a 0, 21, a 12, and a 3. Row 1 I did use, but I didn't change. And what's so efficient about this, it tells me exactly which rows change at this stage. So every time we're doing Gaussian elimination, that's what we're going to do. We're going to make those two 0 in the first step. The second step, we're going to make that a 0. How do you do that? You have to use those two only. If you use the first row, you alter the zeros back, you run into a loop. So it has to be between those two. Well, if I multiply this row by a negative 3, so take negative 3 row 2, add it to row 3, and since I want the 0 right there, put the result in row 3. So always 2 steps. In the beginning, this seems to be like a lot of work, but you'll pick this up. It's not that bad. If I multiply a row 2 by a negative 3, this by a negative 3, that will be 0, negative 21, negative 12, and negative 3. Add it to the third row. If I copy the third row down, what am I looking at? I'm looking at 0, 0, that's a 6, and that's a 0. So in this case, I would know that. I can see clearly, well, I was just looking. That's a 12, not, okay. I was going to say this is 0. But that's a 12, so when you add them, actually that's a 0. Okay, well, again, if I make a mistake, you get the idea of what we're doing. Well, how are we going to say this? We're going to say the last column, 0, x3 equals 0. That means x3 could be any number. Let's say that t. Put t in there. Wouldn't that mean that x2 is 1 minus 4t divided by 7? And we know that 2x1 plus 2 times x2 plus 2 times x3 equals 0. If I clear the fraction, 14x1 plus 2 minus 8t plus 14t equals 0. 14x1 equals, that is, what is that? That's 6 plus 2 minus 6t equals 0. So x1 would be 2 minus 6t divided by 14. You could put it as an ordered pairs if you want, that doesn't matter. But eventually we're going to start writing those as vectors, and they're going to look like, sorry about that, that was my phone. All right, next problem up. Determine whether the homogeneous, remember what homogeneous system is, something we're going to have to learn in the long run. Homogeneous system is when all of these are zeros. That's a very special case because no matter which operation you do, those zeros never change. You multiply 0 by a number, it's 0. You add it to another 0, that's always 0. They say determine whether the homogeneous system have non-trivial solutions by inspection without pencil and pen. Okay, well, looking at it, I could tell that x3 is 0. If I put 0 right there, x2 is 0. And if I put zeros right there, x1 is 0. So I could tell the only solution to this problem is 0, 0, 0. That's called trivial. We haven't talked about that, but let's get that out of the way. So if I told you, give me a solution to a plus b plus c equals 0, well, you could say the most basic thing that everybody hopefully knows, that let a equals 0, b equals 0, and c equals 0. We call that trivial. What we're looking for is non-trivial, a solution other than that, something like a equal 1, b equal -1, and c equals 0, for example. It's just an example. That would be a non-trivial solution. Here's another system right there. Solve the given linear system by any method. Okay, well, this is linear, right? That means all of these are zeros. And we'll talk more about that when we meet next time in class, how this plays. Let's solve it. If I want to solve it, this is 2, -1, -3, -1, 2, -3, 1, 1, 4. Now, you will notice in the book, or if you look at their examples, they really don't write this. And the reason they don't write that, not because it's not there, because there's nothing you could do to change the zeros. I'm going to play along and put those zeros there and show you that it's always 0. So whenever they're solving this system and they write it as an augmented matrix, they drop that 0 column because that's always going to be 0. And at the end, they bring it back and say, let's solve it and see what happens. So what's the goal? Again, I want to make this a 0 and this a 0. Well, if I want to make this a 0, I'm going to take row 2, add it to row 3, put the result in row 3. Let's see what happens. If I multiply, and here, let me play along just to convince you. If I add those two, I'll get a 0, a 3, a 1, and 0 plus 0 is 0. Now to make that a 0, I'm going to take a row 2, multiply it by 2, add it to row 1, and put the result in row 2. Notice I'm multiplying this by 2, add it to that row, but the result is going to be right there, and that's going to give me the 0 that I want. So if I multiply row 2 by 2, that will be -2, a 4, a -6, and a 0. Row 1 is 2, -1, -3, and 0. If I add those, I'll get 0, 3, -9, is that right? And a 0. And row 1 we just copy down. Now what's the next step? Use those two rows to make that a 0. Well, I could do that. Take negative row 2, add it to row 3. Okay. Sometimes it erases, sometimes it doesn't erase. Take negative row 2, add it to row 3, put the result in row 3. So I'm looking at oh, I messed up. If I multiply row 2 by a negative, that becomes 0, -3, 9, and a 0. Add it to row 3. I'll be looking at 0, 6, 0, 0, 10, and a 0. Well, do you notice that means x3 is 0? Oh, z. They use, I'm so stuck on x1, x2, x3. It's z in this case. Z is 0 because that says 10z equals 0. So z is 0. Well, if z is 0, that means y is 0. And if both of these are 0, that means 2x equals 0. That means x equals 0. We get the trivial solution. That's something we're going to hunt for later on in the course. Notice if these are always 0, then one of two things happen. Either you get all of them to be 0 or you get no solution or an infinite amount of solutions. So the solution that you get will be only the zeros if there is a solution, right? That's the only solution that exists. Or you can have an infinite amount of solutions if those zero out, right? but I did say you get no solution. It's impossible to get no solution. You can't. The reason you can't get no solution in this case, because if you take any number and multiply it by z and it equal to 0, if this is 0, then 0 equals 0 will be the infinite amount of solutions. And if a doesn't equal 0, then you're going to get z to be 0 and there's a solution. So whenever you set this to be the trivial, the homogeneous, it's one of two things. Either you have the trivial solution 0, 0, 0, or you have an infinite amount of solutions. But there's no way of getting no solution. The only way you can get no solution if you had it backwards. If you had 0 equal 10. This says 0 times z equal 10, but 0 times any quantity is 0, and that's the only way to get no solution. We'll talk more about this as we move on throughout the course. Next set of problems, we just want to talk about what this means. Again, a bit of theory. The augmented matrix, this is augmented, that means, so you want to know, is it just a general matrix or augmented? The augmented matrix stands for a system of equations for a linear system is given in which the asterisks represent an unspecified real number. Those asterisks could be any numbers. You don't know what they are. Could be 0, could be 10, could be negative 10, pi, whatever. Determine whether the system is inconsistent, and if so, whether the solution is, determine whether the system is consistent, and if so, is the solution unique? That means, do you get only one solution? Answer, inconclusive if there is not enough information to make a decision. Now, A, there's a solution right there, right? Say that x3 equal 1. If you plug it in, no matter what this number is, x1 will work. So this has a unique solution. B, no matter what this number is, x3 equal that. x2, no matter what that number is, you could pretty much, let me think really, let me go backwards. I misspoke. Okay, let's go this way. x1 is whatever that value is, right? So there could be 0, it could be 5. Once I know what x1 is, I could figure out x2, right? Plug it in and figure out whatever that number is. And once I know those two, I could figure out s3. That would be a unique solution. Here we're just doing things backwards. Now, if I look at C, in C we have a problem. This is inconsistent. And the reason for that, here it says x1 equals 0. And here it says x1 equal 1. You can't have two solutions for x1. That's inconsistent. That's the no solution. And if you really want to see it, take negative row 1, add it to row 2. Row 2 becomes 0, 0, 0, and a 1. That says 0, x3 equal 1, but 0 times any quantity is 0, and there's no solution. Okay, D, there's not enough information because it only tells you that x1 is 1. That's what it says. It says x1 is 1. Put a 1 there. You don't know whether those have a solution, no solution, an infinite amount of solutions. And that's pretty much what this section is all about.